Hello and welcome to this video on isomers. Isomer is a broad term from chemistry. It relates to the structure and combination of elements in a molecule. Isomers are the same combination of elements with the same bonds, but a different three-dimensional orientation. These are called stereoisomers, or it could be the same components rearranged slightly. These are called constitutional or structural isomers. These are just two of a number of different forms that an isomer can take. The change in direction for an isomer is denoted by either a D or an L prefix, and further isomer variations by a beta or alpha prefix. Isomers are a major element in brewing, with a range of sugars being isomers of one form or another. Isomers are important because most molecules act very much like a Lego block. The difference in orientation of molecules, like saccharides, changes the shape of the two molecules, despite being made from the same components. Rather like trying to use the same block to connect it to the back of another. This simply would not function. In other cases, it is like mixing different brands of building blocks. They may not necessarily match and work together. This is a seemingly minor change to form and function, which can be further reaching than you realize. The difference between L and D molecules is exemplified by the taste of oranges and lemons. Limonene is a flavoring molecule of citrus. The D isomer is responsible for the orange flavor, whilst the L isomer is responsible for the taste of lemons. The reason behind this small change and the huge effect is how it fits into a distinct receptor in the human nasal cavity. From here, it works in a unique cascade of events, triggering the brain into thinking it is one or the other. Each receptor has a unique fit, and so the isomer is important. The L or D prefix describes the direction of the mirrored compound, L for left and D for right. These designations are used for molecules with more than one carbon, not in a linear chain. This is common in carbon rings. The importance of isomers becomes more apparent when you use sugars. Take this image for example. One is alpha glucose and the other is a beta glucose molecule, but would you know the difference without either specific knowledge of this or searching for the difference? Alpha and beta glucose also form galactose and mannose. That is 6 possible conformations of one chemical description, that being C6H12O6. 6 carbons, 12 hydrogens and 6 oxygens. These compounds are examples of constitutional isomers. Again, without knowing which is which, have you been able to figure out which molecule belongs to which name? This is the same problem with sucrose, lactose and maltose. The rest of this video will be limited to the two broad isomers mentioned, constitutional and stereo. You should note that several other categories exist to further divide and describe isomers. In brewing and applications of sugar, the L and D prefix is important. Only the D glucose molecule can be metabolized. Adding an unfermentable sugar may or may not play havoc with your brewing. It introduces a range of issues from osmotic pressure to competitive inhibition and more. It might also be a useful tool if you need to add body or sweetness without alcohol. You can see here what small changes indicated on each of the isomers. Between a dextrose and a glucose molecule, there's been a small movement in the hydroxyl group. The hydroxyl group went from pointing in one direction to another. Individually, this may not mean much to you, but it will in the big picture. A chain of alpha-glucose molecules makes starch. A chain of beta-glucose molecules makes cellulose. One of these is digestible by yeast, whilst the other is largely not. The importance of alpha and beta glucose is seen when long saccharide chains like cornstarch or cellulose are used. You may not think either of these are going to be anywhere near your brew, but you would be wrong. Starch is in barley and wheat for beer, and cellulose is part of the aging process. Isomers can further alter the use of sugars and many other processes. The alpha-glucose chain is defined by the position of the hydroxyl group bond. This puts the molecule in the down position. As an example, this creates a bitter-tasting mannose. Meanwhile, the beta chain is defined by putting the molecule in the up position. This makes mannose taste sweet. These are the same molecule, with slightly different positioning relative to everything else, and yet it has a substantial effect on the taste, and as a consequence, if you are brewing, a substantial effect upon your brew. Now that you have some understanding of the surrounding information for isomers, we can discuss the two primary types. First is a stereoisomer, and this is the easiest kind of isomer to understand. Think of this as being like a die. A dice has a fixed face with a set value. This will be that all two opposing sides add up to 7. You can rotate the dice in space, with a different face pointing out each time, but it will never change the relative position of the dots on each side. This is a stereoisomer. The positions of each part of the compound remain in the same position as with the dice pair of opposing sides. No matter which way you rotate it, they will always remain in the same relative position, and this can be translated to the chemistry of a stereoisomer. The structure remains the same, but the compound is rotated in 3 dimensions. This means the same formula and skeleton of connections between each molecule remains constant. Stereoisomer is an overarching term for a further 5 subdivisions. These define the different ways the molecule is rotated or structured relative to certain carbon units within it. A constitutional isomer is different to this. It is a case of the same molecular formula, but with a different structure of connections. Galactose is C6H12O6. Glucose is C6H12O6. In fact, you can add galactose to this list with the same chemical formula and have 3 sugars with the same chemical formula but different structures. The same chemical formula can extend to another 80 or so sugars. Outside of sugars, the same formula is used for a number of other isomers. Despite this, when you draw out the arrangement of each molecule, it is different. This change in arrangement has an effect on the physical and chemical properties, and that is why these are considered different compounds, but also an isomer of the same chemical formula. There is one important note to make here. Do not make the mistake of confusing the linear diagram and the ring diagram of the same molecule as different compounds. The overall shape is largely redundant, as each depiction is used to understand the configuration and relative position of the parts of the compound, but it is largely irrelevant if it is linear or ring-shaped. Yeast can break open these rings as needed, or the environment may cause the conformation to change. In either case, for brewing, the open or linear nature is largely unimportant, but it is worth remembering that, depending on how it is depicted, this may either be a linear sugar or a ring sugar, and in an environment, the sugar may form a ring for stability. Now, you may not need to worry about isomers in everyday brewing, but the introductory information here can be helpful for those wanting to experiment. Most naturally occurring sugars are of the D-isomer variety, which is biologically active. More important for brewers is how and why of separating sugars from the compact storage form, this being the ring. Thank you for watching this video. If you have found it useful, consider liking, sharing, and subscribing. Please post any comments, questions, or suggestions below.